So I've just been over there, just across the car park, and you can see the rig. It's not a great big oil and gas rig, it's a kind of modest thing. But I've also had a look at the core, and if you don't know what core is the rock that the drill extracts from the hole. And I've just had a look at it. It's amazing. I mean, this is a slightly nerdy comment, but I've never seen such good core. They've cored, sorry for that. They've cored through a coal seam, and it's a perfectly shiny piece of coal. It's absolutely wonderful for a scientist to work on. And we're going to take this down to the core labs in BGS. So we've got a new CT core scanner, an X-ray diffraction core scanner, and we're going to core scan that stuff. So we'll be able to do some really amazing science on this. And as Zoe has said, it's really about understanding what the subsurface is doing, what it can do for us, and how we need to look after it. So I'm Director of Science and Technology at BGS. One of the ideas I've always pushed is the idea that we need a geological macroscope, not a microscope, but a macroscope. And you might ask, what's that? Well, it's the idea that very big things can be understood and studied with lots of sensors, with lots of machines and measuring devices. So, for example, we already have a meteorological macroscope. It's called the weather system. It's the stuff we use to measure and observe the weather system. So the UK Met Office has a macroscope that looks at the atmosphere and measures it, and it comes up with a weather forecast, a 3-day weather forecast. We can do that because we measure with huge numbers of sensors all over the world what the atmosphere is doing. We also have an ocean macroscope, and then one of the reasons why people like David Attenborough have been able to point out the problem with plastics in the oceans is because we measure and observe oceans with enormous numbers of devices that sense what's happening in the oceans. If we didn't do that, we wouldn't understand the ocean like we do. We've still got a long way to go, but we wouldn't understand it as we do. But we don't have a macroscope for the last thing, which is that underneath this. We don't have a macroscope for that. What we have is places where we do measure what's happening in the earth, some places near volcanoes where there are lots of earthquakes, but generally we don't have that. So we don't have an understanding of the earth in the way that it behaves year by year or day by day or second by second, like you do the atmosphere or the oceans. So this is really, what we're doing here is a start to understand the subsurface better. It's a small start, and the site in Cheshire is adding to that, but essentially we are putting together a geological macroscope. And the reason why we're doing it now is because it's actually been harder for us to do it than meteorologists and ocean sensor people, oceanographers. And that's because the kit that you need, the sensors have to be tougher, because they've got to be down the bottom of deep boreholes, because they've got to be able to take quite warm temperatures or hot temperatures, because they're a long way from the surface. But those sensors are coming about. They're being created. These are devices that can go down boreholes and test the temperature of groundwater or the chemistry of the groundwater or seismology, for example. Those are coming up. We also have huge computing power that we didn't have before. We also have the ability to visualize the subsurface in ways that we never had before. Using computers, we can project images of the subsurface, stripping away the rocks so that you only see certain layers. And we have a fantastic facility in BGS in Keyworth that does this, and us also now in the Lyle Centre. So we have those three things, those three technologies have made it possible for us to do this geological macroscope. We didn't have it before. And the geological macroscope that we're doing here, the UK Geoenergy Observatories, it's quite hard to say, is essentially aiming at decarbonisation. It's essentially aiming at the idea that Zoe and David have just said, that we do need energy, we are an energy-hungry society, but we also need it without producing lots of carbon dioxide. It's a very simple problem, but it's not an easy problem to fix. And my idea has always been, if you want to decarbonize, you need the underground to help you, because the underground is going to supply a lot of the technologies to decarbonize. I know that wind turbines will, and I know that solar will, but we will need the underground too, because, for example, of geothermal. Because, for example, we might need to store or dispose of carbon dioxide and carbon capture and storage. Because in renewable technology, in renewable energy, there's a an intermittency problem. Sometimes we make too much renewable energy. Sometimes we have too little. And so we need to be able to smooth out that supply of energy. We can do that by using grid-scale energy storage. And one example is compressed air energy storage, a fascinating idea. Hydrogen storage, Zoe mentioned hydrogen is a fantastic vector for energy. We could use that, but we'll need to store it underground, because if we are going to go to hydrogen economy, we need a lot of hydrogen. The same with geothermal on the far right there. Geothermal mine water heating is a big thing, and that's what we're going to be doing here in Scotland. So how did we choose these sites? So Zoe mentioned that we wrote a science plan. We got some of the top minds in the UK, geoscience minds in the UK, to write that science plan. That science plan was our Bible. It was the thing that we used to design the things that you're seeing over there, the structure that you're going to see and the structure you could see in Cheshire. But essentially what we needed is places which had a lot of geological data, so that we could already make a good choice about what rocks there were in order to test what technologies we want to use. We also wanted a range of different geology types. And geology is very variable in the UK. But in fact, here in Scotland, we'd have a particular geology which is really perfect for checking this mine geothermal idea. We also wanted a place or places that were representative of the UK, so that the stuff that we worked out, so the technologies and the science that we do, has some bearing on other parts of the UK. So it's not just solving the problem for Glasgow, it's solving the problem for other areas. So those are the things that were in our minds. So first of all, why the Cheshire site? And this is a slightly different site to the one you're going to go and see this afternoon. Well, essentially, in Cheshire, what we have is a combination of three really good factors that make it a great place in West Cheshire to do this. We have, first of all, the Sherwood Sandstone group. This is the upper sandstone layer that sits underneath most of Cheshire, which is a principal aquifer. It's a really important supplier of groundwater. It's the second most important aquifer. That's the sort of thing we want to protect, because we need groundwater. And it's also a place where we might get geothermal as well. We have a barrier cap rock, a barrier between essentially an energy level, which might be the coal measures, the millstone grit, the shale that's deep down in West Cheshire. And we have essentially here the sorts of groups of rocks that enable us to do a lot of really, really good experiments on energy activity. But I'm not going to concentrate on the Cheshire site. I'm going to have a quick look at the Glasgow site. And I'm kind of repeating what Zoe said, but it's a really important point. And here's the site. We're going to have a look at it in a minute. First of all, it's underlain by old coal mines that could yield their heat. We've heard a lot about this. It doesn't sound very dramatic, 10 to 15 degrees C, but it's there all the time. And there's an awful lot of it. There's kilometers cubed of rock which is at that temperature. We're not talking about a small amount, we're talking about a lot of warmth. So the questions really are important. What we're going to do over there is pretty simple. We're going to say, is there enough for houses and businesses? We don't know at the moment. We actually don't know how much heat there is. Secondly, what's the best way of getting it out? So he mentioned these reverse fridges. There may be different ways of configuring these to make it better. Perhaps the most interesting one is how fast is the heat replenished? So when you take it out, does it come back again quickly? Because if it doesn't, then effectively you're mining the heat, which you don't want to do. You want that to be completely renewable. And so that is a really important question. How fast does the heat come back when you've pulled the heat out of the ground? And this is what it's going to look like. It's actually going to be really inconspicuous at the surface. I'm working for 3 or 4 years on this, and one of my kind of regrets is there's not going to be a great big wonderful shiny building or a Jodrell bank or an enormous telescope or reflector at the top. There isn't. There's going to be a few very modest little boxes at the surface. But essentially there are 4 or 5 deep boreholes that are going to go down into the subsurface, and they're going to enable us to do experiments. So things like, for example, does heat move from one borehole to another quickly? When you take heat out of one borehole, what happens to the heat in the one nearby? So these sorts of basic experiments, basic applied geoscience, it's looking at how feasible this area is. And what we essentially are doing is looking at how feasible mine water heat is, how practical it is. At the moment, it's very difficult for companies to take the plunge and do this because it's expensive, it's complicated, there are risks. But here we are doing some basic science to see if it can be done. And that could be a market failure thing in the sense that it might encourage geothermal to develop, because we'll be looking at the science, the basic science of how fluids move and how heat moves in the subsurface. So it's going to be really important. And as Zoe said, this is all about science. You know, it means the local universities will benefit. Local school children could benefit. This is bringing practical science, applied science, to people who really are going to benefit from it. It's not Brian Cox. It's not that. But it's still pretty good stuff, you know, because it's very practical. And it means heating. Maybe it is Brian Cox. Maybe we can get him here. I don't know. Possibly. So the schedule is fairly simple. So we'll start. We've got planning permission already, as we know. We're already drilling. It began on the 14th of November. We're going to complete construction within a year. We're going to decommission at the end of the life. I mean, we say 15 years, 20 years. I hope it's longer than that, because I hope it will bring in scientists and investment, and we'll keep it going and keep solving problems and keep looking for solutions to the things we need to find solutions to. We'll decommission, and that means we'll make sure those wells are completely sealed so that, you know, they are essentially just intact rock again. We'll also remediate the land after use, so you won't actually be able to see anything. There'll be nothing there. But I hope our system, the thing we set up here, lasts for a long time. And these are unique. Both of these observatories are unique. We're enabling long-term observation of the subsurface in great detail. This is ambitious science. This is our CERN. This is our Jodrell Bank. This is our diamond light source. It may not be as big and beautiful to look at, but it's essentially tackling big problems that we need to solve. And we aim at co-funding and partnerships so that we bring the best universities from the UK, from across the world. We want government to be investing in it, and we also want industry as well to be investing. I'm nearly at the end. One of the big things that I wanted when I was writing the early versions of this project was that this is data and science that should be available to everyone. So what I really want, and I think everybody wants, is that every part of the data, everything that we measure, is available to the public via the web all the time, as much as possible in real time. It may not be very interesting to people to read about the temperature of their groundwater or the quality of it, but I think it's showing the collection of data, and I think school kids and physicists, people in studying physics at school and chemistry at school might use that. We'd like it for scientists too. So some of the great scientists in Scotland, we've got here in Scotland some of the best CCS scientists in the world, some of the best geochemists in the world working in the subsurface. That data is going to be there for them. And for industry too, because this is really partly about market failure. It's about addressing some of the things that the industrial partners can't really do, but we can do because we're producing the science that will help them. And we're already doing this. BGS has excellent experience in monitoring, observing, and putting information on the web in real time. And you can actually log on to various sites which show our seismicity monitoring and our groundwater quality monitoring, for example. And I think that's the end.